Hi boys and girls, this is lecture 7.4. The topic, Differential Equations, Growth and Decay, Part 2. Today we're going to look at a few more examples of applied growth and decay models. Many real-world phenomena can be modeled by functions that describe how things grow or decay as time passes. Examples of such phenomena include the studies of populations, bacteria, the AIDS virus, radioactive substances, electricity, temperatures, and credit payments, to mention a few. Any quantity that grows or decays by a fixed percent at regular intervals is said to possess exponential growth or exponential decay. Exponential growth and decay are mathematical changes, and the rate of the change continues to either increase or decrease as time passes. Let's start with radiation. Since the rate of decay is proportional to the function, we know that the solution will take the form of the exponential decay model y equals c e to the kt. So let's examine the problem for the initial conditions we'll need to solve for c and for k. Suppose that 10 grams of the plutonium isotope 239Pu was released in the Chernobyl nuclear accident. That means at time t equals 0, 10 grams were released. How long will it take for the 10 grams to decay to 1 gram? So ultimately, we'll be looking for at what time will we have 1 gram of this isotope. But we need another initial condition, and that's given to us here. The half-life of 239Pu is 24,100 years. So for this 10 grams to decay to 5 grams, the time will be 24,100 years. That's our second initial condition. We'll be able to use these two initial conditions to solve for C and K. Once we have our specific solution, we'll be able to find the time at which the isotope will be 1 gram. So let's start with the initial condition 0, 10. 10 equals Ce to the k times 0. This means 10 equals Ce to the 0, which means C equals 10. So we've used our initial condition 0, 10 to solve for C. This means our solution is now 10 e to the kt. Now let's use the second initial condition to solve for k. 5 equals 10 e to the k times 24,100. Dividing both sides by 10 gives me 1/2 equals e 24,100k. We're going to need to take the natural log of both sides. This gives me the natural log of 1/2 is equal to 24,100k. Dividing both sides by 24,100 gives me natural log of 1/2 over 24,100 equals k, and that is approximately equal to negative 0.000028,761. So here is my specific function. Y equals 10 e to the negative 0.00028,761 t. Now let's use this function to find when the isotope will decay to 1 gram. 1 equals 10 e to the negative 0.00028,761 t. Dividing both sides by 10 gives me 1/10 equals e to the negative 0.00028,761 t. Taking the natural log of both sides, I end up with the natural log of 1/10 is equal to that number that I keep saying over and over and over again. Dividing both sides by that number gives me the time. 28761 equals t, and that is approximately 80,059 years. That's how long it will take our 10 grams of the plutonium isotope to decay to 1 gram. In this example, we'll see how the exponential decay model can be applied to declining sales. 4 months after it stops advertising, a manufacturing company notices that its sales have dropped from 100,000 units per month to 80,000 units per month. In this first sentence, we have both initial conditions. At time 0, when the company stopped advertising, they were selling 100,000 units per month. 4 months later, they were selling 80,000 units per month. We'll use these two initial conditions to go from the general form of the exponential decay model to a specific form applied to this particular scenario. Then we'll answer the last question. If the sales follow an exponential pattern of decline, what will they be after 2 months? Well, let's use the initial conditions to find the specific solution first. We'll start with 0, 100,000. 100,000 is equal to CE to the K times 0. As we've seen before, this means that C is 100,000. Thus, our solution, y equals 100,000 e to the kt. Now let's use the second initial condition to solve for k. 80,000 is equal to 100,000 e to the k times 4. Dividing both sides by 100,000 gives us 4/5 is equal to e to the 4k. Taking the natural log of both sides gives us natural log of 4/5 is equal to 4k. When dividing both sides of this equation by 4, we end up with k is equal to -0.0558. So now we have our specific solution. Y equals 100,000 e to the -0.0558t. We'll use our specific solution to find sales after another 2 months. Of course, that will be at time 6 months. So, using our equation, y equals 100,000 e to the -0.0558 times 6. Based on this model, after 6 months, our sales will be 71,500 units. In this example, we'll apply the exponential growth model to bacteria growth. A certain type of bacteria, given a favorable growth medium, doubles in population every 6.5 hours. Given that there were approximately 100 bacteria to start with, how many bacteria will there be in a day and a half? As we know, the general solution will look like this. Y equals CE to the KT. But we'll need two initial conditions to solve for the specific C and K, and they are given to us in this problem. Notice that initially there were 100 bacteria, so at time 0, we had 100 bacteria. We're also told that the population doubles every 6.5 hours, so at time 6.5, the population was 200. Once we use these two initial conditions to solve for our specific function, we'll find out how many bacteria there will be in a day and a half. Let's start with 0, 100. 100 equals CE to the K times 0. This means C is equal to 100, giving us this equation. Y equals 100 e to the KT. Now using the second initial condition, we'll have 200 is equal to 100 e to the k times 6.5. Dividing both sides by 100 gives us 2 equals e to the 6.5k. We'll need to take the natural log of both sides. This gives us natural log of 2 is equal to 6.5k, and dividing both sides by 6.5 means that k is approximately equal to 0.107. Now our function looks like this. Y equals 100 e to the 0.107t. This is our specific function, and we'll use it now to find out how many bacteria there will be in a day and a half. A day and a half is 36 hours, so we're going to solve for the number of bacteria after 36 hours. At that time, there will be approximately 4,648 bacteria. That's it for today's lecture. Here we have a depiction of the enduring and epic battle between genders, I mean number systems. God bless you, boys and girls.